Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over why the percent dissociation of a weak acid or base will increase as the concentration of that weak acid or base decreases. So let's get into this. So first thing we want to do is write out our uh, generic equation for a weak acid. So HA dissociates, or the proper term is not dissociate, but to actually ionize, since your acids are actually molecules. So they will ionize and become ions in solution. So dissociation is not really the correct term, but we're going to go ahead and use it anyway. Dissociation is usually used for, say, ionic substances that where you actually have ions and they separate in solution, and so we say dissociate rather than ionize. So here the correct term would be ionize, but I'm going to use dissociation anyway. So just to get that out of the way. So here's our equation. So therefore, the percent dissociation is going to be defined as the concentration of the ions over the concentration of the undissociated or unionized acid, the weak acid, multiplied by 100. And so in this case, the ions here are H plus and A minus, and the undissociated is your HA, the acid that is still intact. So you can see that this percent dissociation equation is like the Ka, right? So your Ka value, the equilibrium constant, is the concentration of the ions, H plus, times A minus, the anion that's left over after the ionization, divided by the concentration of HA, which fits this kind of equation here. So if we take a bottle of our weak acid and then we double the volume by adding a double amount of water, then what happens to the concentration of all the species in the solution? Well, they're going to be cut in half, right? So you double you double the water, you double the volume, you half the concentration. That's your your molarity times volume gives you the number of moles. M1V1 equals M2V2, that dilution equation. So if you double the volume by just adding water to your acid, you're going to cause the concentrations to be cut in half. And so if we take our Ka, which now would not be at equilibrium because we changed the concentration, so this would be our Q now. So Q is equal to 1/2 the original concentration of H plus times 1/2 of the original concentration of A minus, divided by 1/2 the original concentration of HA. So if you start canceling out your halves here, so that half would cancel out with that half, then you're left with 1/2. So Q then is equal to 1/2 times the concentration of H plus times the concentration of A minus over the concentration of HA. Well, if you come back to Ka, well, Ka is equal to this. And so we have Ka here, right? So this part is Ka. So Q then is equal to 1/2 Ka. So this means that Q is no longer equal to Ka, which is where you would be at equilibrium. So Q is actually less than Ka. It's 1/2 of Ka. Well, what does that mean if Q is less than Ka? Well, that means that we don't have enough product, right? So this, remember, our products are on top, our reactants are on the bottom. So if Q is smaller, that means that this denominator is larger and this numerator is smaller. So we don't have enough products and we have too much reactant. Well, if that's the case, then according to Chatellier's principle, then we're going to shift right. So this reaction is going to shift towards right to make more product in order to reach equilibrium again. Well, what are the products? The products, again, are H plus and A minus. Those are the ions. So we're making more ions. So here, making more ions means that we're going to have a higher percentage of dissociation. More of your HA, more of your weak acid is going to dissociate. And so if we look at our equation again from here, so our percent dissociation is going to be equal to the concentration of our ions, which is increasing, right, to make more product. And our undissociated concentration is going to decrease because our undissociated is now going to dissociate or ionize more. And so if our numerator is increasing, our denominator is decreasing, then that means that this percent dissociation is going to go up. So we're going to have a bigger number here, which means we have a larger percent dissociation. So, and that's why even though you increase, or if you decrease or increase, that's why even though you decrease the concentration of your acid, your weak acid or your weak base, the percent dissociation is actually going to increase. So I hope this was helpful. If this was helpful and this was like interesting for you and you learned something, then please, by all means, like this video, hit that like button, share it with your friends. Also, subscribe to my channel. Make sure you hit that notification bell up above or wherever you located now these days. Make sure you hit the all button so that way you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I'd love to hear from you. Thanks for joining me and have a great day.